We have a pulley problem here. Hopefully pretty obvious that we're going to use an analysis of forces. Anytime you look at forces, your very first step should be to draw a free body diagram. So let's do that. So a diagram of the 102 Newton weight would have its weight of 102 newtons, always pointing toward the center of the earth for the weight vector. There's going to be a normal force that's touching the incline, and so the normal force is perpendicular to the surface. There's going to be a tension force, which is up the incline. There is going to be a friction force, but at least at first it's not immediately obvious which way that friction force points. What we have to do is figure out whether the tension force is stronger than the x component of the weight, or whether the weight is stronger than the tension force. Whichever one of those is stronger is going to tell us which way this has a tendency to move, and then friction always points in the opposite direction that something has a tendency to move. So I'm going to wait on drawing in friction. I am going to draw a tilted axis. Remember, one of the really important things about analyzing forces is that one of your axes always needs to be parallel to the acceleration. That way, acceleration appears in the equation for one of your directions, but then the acceleration is 0 in the equation for your other direction, and that makes math much simpler. The other thing to remember is that when you have an inclined plane problem, the angle that the incline makes with the horizontal is the same as the angle that the force of gravity makes with the axis that is perpendicular to the incline. That's the axis that has normal force on it. That's a good thing to memorize. I mean, you can always prove it to yourself. I'll do that real quick here by drawing the force of gravity. So that actually creates a little triangle right here where this would be the complement of 40 degrees. That would be a 60-degree angle. To complete that triangle, let me draw my y-axis. And I don't know if you can see, but it makes a very tiny triangle in here. And if you look very closely at that tiny triangle, then this angle and that angle, they're called vertical angles, and they're the same as each other, which means that that angle right there, which is the same as that angle right there, has to be the complement of this 60-degree angle. So it's a 40-degree angle. Actually, I shouldn't have said a 60-degree angle. That's a 50-degree angle. Nevertheless, this one right here would be a 40-degree angle. Okay, so again, there's friction here, but I'm going to wait on that. Let's draw the free body diagram of the other object. So that's just going to be 32 newtons pointing downward and force of tension pointing upward. And so now probably the next step, whenever you have a force that is at an angle to your axes, you should always figure out the x and y components. And let me do that carefully. Let me draw this picture a little bit larger here. So there's our 102 Newton weight vector. And here's the y-axis, and here's the x-axis, and here's that 40-degree angle. Sometimes people have a hard time knowing how to draw the x and y components. Sometimes people will draw it like this. And so this weight vector is actually not the hypotenuse. But what you always want to do is have your x or y components perpendicular to the x or the y axis. So, this x component right here is perpendicular to the y axis and it's parallel to the x axis. And maybe that's a better way to say it, that the x component has to be parallel to the x axis. And so that shows us this line right here, the other leg of the triangle, that's parallel to the y-axis. That's the y component. You could also draw it from this direction. One way to do it is take the tip of the arrow, and it's called dropping a perpendicular. Drop a dotted line that is perpendicular to the axis that you're heading toward. So that defines the length of the x component, and then this defines the length of the y component. So these two are the same as each other. These two are the same as each other, whichever is more convenient to figure out. So now actually calculating the x component here, since it's opposite the 40-degree angle, I'm going to use sine. So I have the sine of 40 equal to opposite over 102. So 102 sine 40 equals opposite. Do that on my calculator. Funny story. This is the second time I did this video because the first time my calculator was in radians mode. And so it's a funny story, but it's a good lesson. Always make sure your calculator is in degrees mode or whatever type of angle you're actually using. Anyway, it looks like 65.6, let's say, is the value of the x component, 65.6 newtons. So I can draw that into my picture right here, 65.6 newtons. And I might as well complete this and find the y component as well. The y component is adjacent to the 40-degree angle, so cosine of 40 equals adjacent over 102, so 102 cosine 40. Let's see what that's equal to. 78.1. So I can draw into this picture right here, 78.1 newtons. Now, one other aspect of a pulley problem that's really important is being consistent about positive and negative signs. The tricky thing about a pulley is that the string changes the direction of motion. This object is moving diagonally, this object is moving up and down. So you really are always want to use the string as one of your axes, and what you're really looking at is all of the forces that are parallel to the string. Those are the forces that are going to make the string accelerate. The forces that are perpendicular to the string, they're not going to have any effect on the acceleration of the string. And then we need to be consistent about which direction of string motion we want to call the positive direction. It doesn't have to be the direction that the object is actually moving, because you can have an object moving in the negative direction, but we just have to pick a direction and be consistent. Now in this problem, the textbook itself says choose up the incline as the positive direction. So over here, that's the positive direction. Up the incline is the positive direction. If we continue that around the pulley, that means that over here, downward is the positive direction. So that's just being consistent as to which way is positive. So that means that this force here is a positive force, and this force here is a negative force. This is a positive force. This is a negative force. You can kind of check your work on this, because the two tensions that are connecting the object, those should always be opposite signs of one another. And in fact, now we can get a sense of which way friction has a tendency to point. These two forces of tension basically cancel each other out. So overall, you have 32 newtons pulling the string this way, and you have 65.6 newtons pulling the string that way. So if that's all that's going on, the string is definitely going to move this way. In order to be at rest, if that's the case, friction has to help this weaker 32 Newton force. If this friction always points in the opposite direction of slipping, or the way that something would have a tendency to slip. Because this is larger than this has a tendency to slip this way. So friction is always going to point in the opposite direction of which way something has the tendency to slip. So in part A of this problem, it says that the system is initially at rest. And I think the idea here is somebody's holding on to it and then they let go. So then what's going to happen? Well, that is the hardest problem to solve, because we have to decide whether it's going to stay at rest or whether it's actually going to accelerate. And in order to make a decision about that, we need to know how strong friction needs to be to hold it at rest, and compare that to the maximum value that static friction can have. So first of all, how strong does friction need to be to hold it at rest? Well, let's do this. Acceleration equals net force divided by mass. Let's assume that it's at rest, so the acceleration is 0. Let's add up the forces in the picture. These are the forces parallel to the string. So negative 65.6, positive friction, which we don't know, positive tension, which we don't know, negative tension, and positive 32. And that would be divided by both of their masses put together. And they didn't actually give us the mass, they gave us the weight. So that would be 102 plus 32 divided by 9.8 to get the mass. Although mathematically it doesn't matter, because if we multiply this to the other side, it just becomes 0. So this won't matter. Also, since the pulley is massless and frictionless, the tensions are going to automatically be equal to one another. So what we can solve here for and find out that friction, if it's going to be at rest, we don't know that yet, but friction would have to be 65.6 minus 32. Or in other words, the difference between those two. I can do this one in my head. It's 33.6. So as long as friction is at least 33.6 newtons, this thing will be able to stay at rest. So how do we know whether friction is strong enough for that? Well, we're going to have to calculate the maximum that static friction can handle. So the maximum that static friction can handle is the coefficient of static friction times the normal force. Now they gave us the coefficient of static friction in the problem. And I'm just looking over here, and they say that that is 0.56. But now we have to calculate the normal force. And hopefully you're used to these problems. You can see that we've already calculated the normal force, but I just want to prove it to you. Notice that the normal force is in the y direction, so let's just analyze the y direction. So the acceleration in the y direction is equal to the forces in the y direction divided by mass. And this is, the reason I wanted to do this is just to remind you, this is why we tilted our axis. If this thing is accelerating, it's accelerating in the x direction, which means there is definitely zero acceleration in the y direction. So I can say 0. And then looking at the forces in the y direction, it's just positive Fn and negative 78.1. I'm just looking at this object all by itself. Those are the only two forces in the y direction, divided by the mass, but the mass cancels out with that 0. So yes, the normal, the normal force has to be equal to 78.1 newtons. And so now we can figure out maximum static friction, 0.56 times 78.1 newtons, and let's see what we get. We get 43.76. So think about what that means. The maximum that static friction can exert is 43.76 newtons. Now it can exert less than that. It can exert all the way down to 0. It just can't exert more than that. So how much force did we decide would be needed for this thing to be at rest? We decided friction had to be 33.6 newtons. Well, that is less than the maximum that static friction can handle, 43.76. In other words, static friction can handle this, no problem. Static friction is going to be able to exert that much force. So that was a long way to go, but the answer to part A of this question is that the acceleration would be 0. This thing is going to stay at rest. All right, now let's take a look at part B, which says, what if it's initially moving up the incline? So fortunately, we've done most of the work already in order to answer this question. There's only a little bit that we have to do. Let's go back and look at our free body diagram. So what they said is, let's imagine that this was given an initial upward push. So we know for sure, because they told us, it's moving up the incline. But what that's going to change is the direction of friction. Friction is always in the opposite direction of the way that something is slipping or the way that it's about to slip. The other thing that it's going to change is how big the force of friction is. Since they told us it is moving, then we know that it's definitely experiencing kinetic friction, not static friction. And so we're going to have to calculate how big kinetic friction is. They gave us the coefficient of kinetic friction. It's 0.25. The normal force hasn't changed. It's still 78.1 newtons. And kinetic friction is not like static friction in that it can have different values. Kinetic friction just has one value. If the object is moving, then in this case it's going to be 19.525 newtons. If the object is moving, then kinetic friction is definitely 19.525 newtons. So now if we calculate the acceleration of this system, let's do that. Now remember, when objects are tied together, these two objects are tied together, they automatically have the same acceleration, unless they're tied together by a rubber band. That's the only way that one of them could have a different acceleration than another one. We're assuming that this rope is stiff enough that they move together. And so whenever you have a compound body problem, something that's made up of two or more objects put together, whenever you try to find the acceleration, always do a combined equation, because everything is moving together as if it was one object. And the advantage of that is internal forces will cancel out. Let's see how that works. So let me see. I want to make sure I have both of these in the frame at the same time so you can see what I'm doing here. So starting back here, we have friction in the negative direction. We just calculated that's negative 19.525. Then we have a tension force that we don't know, positive Ft. Then we have a tension force that we don't know, negative Ft. And then we have positive 32. And you know what I forgot, because I put it off to the side here, so it was out of my field of vision, that we also have the x component of gravity. So I have to include that as well, negative 65.6 for the x component of gravity. So 1, 2, 3, 4, 5. Those are all of the forces that are parallel to the string. Now here the acceleration isn't 0, so we do have to divide by the actual mass. And so I'm sure you remember Fg equals mg. We can figure out the mass of each one of these objects. Let's just do that real quick. 102 equals m times 9.8. So that mass is equal to 102 divided by 9.8 is 10.4. And then the other one, which is 32. 32 equals m times 9.8. So that one's mass is 32 divided by 9.8 is 3.27, let's say. All right, so since we're adding up all of the forces on both objects, we need to add up both of their masses, 10.4 and 3.27. Always important that if you're doing all the forces on both objects, you have to do both masses. If you're doing the force on just one object, you just do the one mass. As before, our tensions cancel out, and now we can get an answer here. And let's see what it is. Negative signs are important here. So 19.525, that's negative. 32 is positive. 65.6 is negative. And then we're going to divide by the total mass, 10.4 and 3.27. So I'm getting an answer of negative 3.89. So let's take a moment to think about what that means. Well, the fact that it's negative means that that acceleration points down the incline. Because remember, we said that up the incline was the positive direction. And all that means is that if you do give this thing an initial upward push, it's going to slow down. So as it moves up, it's going to have a negative acceleration, and it's going to slow down, and it's going to come to a stop. Okay, let's lastly do part C. And part C says, what happens if initially it's moving down the incline? So here again, let's go back and look at the free body diagram. Now they're telling us it's sliding this way. And again, friction is always in the opposite direction of motion. So once again, friction is going to point up. But now it's going to be kinetic friction. So now when we add these forces together to get the acceleration, we're going to have, not going to forget this one this time, negative 65.6 plus kinetic friction, which is 19.525, plus the tension force that we don't know what it is, minus this tension force, plus 32, all divided by the combined mass, 10.4 plus 3.27. Tensions cancel out, and we can just put this into the calculator. 65.6, 19.525, and 32. And dividing by 10.4 plus 3.27 gives me an answer of negative 1.03, let's say, meters per second squared. And again, we have a negative answer. What does that mean? Well, the negative answer here means it's going to be speeding up as it goes down the incline because it's moving in the negative direction. If it also has a negative acceleration, then it's going to be speeding up.